All right. Good morning, everyone. I'd like to welcome you all and thank everyone for coming. If needed, you can click on the caption icon. Okay, I am the chairperson of this session, so Shinichi Yamaguchi from STM Research Institute, Keio University. I studied at the MIT and I was a member of Nancy's lab during that time. So today is the second day of STAMP workshop. It's CAST day. CAST is an accident analysis method based on STAMP. We will start with a keynote. The speaker is Professor Nancy Leveson. I'm going to introduce Professor Leveson briefly. Professor Leveson is an American specialist in system safety and a professor of aeroastro at MIT. Professor Leveson conducts research on the topics of system safety, software and system engineering, and human-computer interaction. She developed the STAMP, STPA, and CAST for safety analysis. Regarding her research, she received many awards until now. Okay, welcome, Professor. Thank you for joining us today. So please share your presentation, 15 minutes for the keynote, 20 minutes for questions. Please go ahead.
All right.
Mhm.
Thank you for inviting me. Here, let me get this up here. Can you see this now?
Yeah, I can see it. So it's good.
Okay, so I'm going to talk about how to learn more from accidents. I've been involved in a lot of major accident investigations, but I find that we don't learn enough from it, that many of the causes never get into the accident report and are never considered seriously. So the first question is, why aren't we learning enough from accidents? Well, there are some common problems. And I'm going to talk about each of these, something called root cause seduction and oversimplification of causes, hindsight bias, a focus on blame, a narrow view of human error, and an inadequate model of accident causality. So let's look at these. We seem to assume that there's a root cause of an accident. The fact is, there never is a root cause or even a couple root causes. Why do we like to have a root cause? Because it gives us an illusion of control. We feel like if there's one or two causes, then we can fix those and get rid of accidents, and then we're in control. So we usually focus on operator error or technical failures. We ignore the systemic and management factors. And what that leads to is a process where we fix symptoms, but not the real cause of those symptoms. So we're in continual firefighting mode. We're continually putting out fires and having the same accident over and over again. In fact, in any accident, there's almost always operator error, flawed management decision-making, flaws in the physical design of the equipment, safety culture problems, regulatory deficiencies, and throughout the management and control structure. And of course, you're probably all familiar with that because so much attention was focused on the Fukushima Daiichi a nuclear power plant accident and all the things that went into it. And just blaming that on an operator or on the failure of the power to come on is misses the most important factors, which were cultural, government, and other kinds of flaws. There was a man, Jerome Leder, who is considered the father of aviation safety. And he said that system safety covers the total spectrum of risk management. It goes beyond the hardware, and it involves the attitudes and motivation of designers and production people, employee management rapport, the relationship of industrial associations among themselves and with the government, human factors and supervision and quality control, the interest and attitudes of top management, the effects of the legal system on accident investigation, the certification of critical workers, politics, resources, public sentiment, and many other non-technical but vital influences on whether we are able to gain an acceptable level of risk control. And it's very important that these non-technical aspects not be ignored, or we will not be able to prevent accidents. There's also something called hindsight bias. If you see on the left, before an accident, everything appears very complicated, very lots of information coming in different order and different ways. And then the accident happens in the middle. And then after the accident on the right, you can see it's very easy to see what went wrong. But that wasn't so clear at all before the accident. And you see these words in accident reports: should have, could have, would have. This first quote here in this box is from an accident where an aircraft ran into a mountain in Colombia while coming into Cali, Colombia. And it said the failure of the flight crew to discontinue their approach into Cali, despite numerous cues alerting them of the inadvisability of continuing the approach. The problem is that those cues were only evident after the fact. Only after the accident did those appear to be relevant cues. Before the accident, they weren't. The second is a quote from an accident in a chemical plant. The board operators should have noticed the rising fluid levels in the tank. Note the should have. And so I asked them, and it doesn't explain it. It just says it should have been the operator. So I asked the people who wrote the report, why would the operator know? Because from what I could see, the operator had stopped inflow. Their flow meter said there was no flow. Every indication showed there was no flow into the tank. And they said, well, they could have looked at another screen and found this out. But at the same time, an alarm came from a different part of the plant, and they had to attend to that. There's no reason why everything appeared fine. Only in hindsight did they know there was a problem. So after an accident, it's very easy to see where people went wrong, what they should have done. It's easy to judge about the people missing a piece of information that later turned out to be critical. Easy to see what people should have seen or avoided, but it's almost impossible for us to go back and undo what we know in our mind, understand how the world looked to somebody that doesn't have knowledge of the outcome. So to learn, we need to identify not what people did wrong. That gives no useful information. We need to ask, why did it make sense for people to do what they did? Nobody comes to work, or most people, 99% of people do not come to work and say, get up in the morning and say, oh, good, I'm going to work. I'm going to kill myself and other people today. They're all trying to do the right thing. Everybody is trying to do the right thing. So the question is asked, the question we want to know is, why did it make sense to them at the time to do the wrong thing, what turns out in hindsight to be the wrong thing? The question arises, we all have heard operators cause most accidents. And is that true? Well, operators are blamed for most accidents, but that doesn't mean they really cause the accidents. So in the traditional view, we assume that operator error is the cause of accidents. So what we should do is something about the operator, fire the operator, retrain the operator, do something about them, or do something about operators in general, marginalize them, put in more automation so they're farther away from the automation and more likely to make mistakes, or rigidify their work by creating more rules and procedures that they can't follow and won't be able to follow. Fumbling for his recline button, Ted unwittingly instigates a disaster. The new systems view of operator error says that operator error is a symptom. It's never a cause. All behavior is affected by the context in which that behavior occurs. But the role of operators in our system is changing. They're supervising rather than directly controlling. They're supervising automation. Systems are stretching the limits of comprehensibility. They're so complex that it's almost impossible for the engineers don't understand them all. So why would the operators be able to? We are in fact designing systems in which operator error is inevitable, and then we blame the accidents on the operators rather than blaming it on the designers. So to do something about error, we need to look at the system in which people work. The design of the equipment, the usefulness of the procedures, the existence of goal conflicts and production pressures. In fact, I conclude that human error is a symptom of a system that needs to be redesigned. Here's another example of an accident report. This was again the Cali report, a Cali aircraft accident. Failure of the flight crew to revert to basic radio navigation at the time when the flight management system, that's the software, assisted navigation, became confusing and demanded an excessive workload in a critical phase of flight. Do you see what's being said here? It's the flight crew's fault for being confused, instead of the fault of the software for being confusing. That doesn't make much sense. It is not going to solve our problems because the flight crew died, and we can't punish them. It doesn't make any sense. We need to fix the navigation software. In fact, blame is the enemy of safety. The goal of courts is to establish blame. The problem is when you focus on blame, people stop reporting errors, information is hidden, everybody points at everyone else. It's someone else's fault, not mine. I can't get this to work on my screen. Learning is inhibited. And so while it may make us feel good to find somebody to blame, we don't learn when we do that. The goal of engineering is to understand why accidents occur in order to prevent them. We need to leave blame to the courts, to the legal system, not engineering. It doesn't help us to find blame. There are two possible goals in any investigation. We can identify someone to blame, or we can find out why the accident occurred. In the first, I call the accusatory approach. We focus on who and why they did what they did. To find out why an accident occurred, we need to look at what happened in the accident and why, and not to focus on who or who to blame. There's also a final problem with our reason we aren't learning enough and preventing accidents is that we use inappropriate accident models. The accident models identify why we think accidents occur. And we almost all have used traditionally a linear chain of failure events. So what we say is there's a chain of events. E1 leads to E2, which causes E3, which causes E4, which causes E5. Each one is the preceding event of the other. We can think of it as a set of dominoes. The problem is that doesn't tell us why the events occur. And we don't learn from that because it's too simple a model. It's not why accidents occur in today's complex system. The events are not enough. Here's some examples. The event, this was a real chemical plant explosion. An automatic protection system was triggered that was designed to prevent liquid from entering the exhaust gas system, the flare. But preventing the liquids from entering the flare also prevented the gases in the system from being discharged, which increased pressure in the reactor and led to an explosion. But that doesn't tell us, that's only superficially why it occurred, the events that occurred. There are all kinds of questions that rise. Did the operators notice this? Was it possible to detect this? Did their instruments show any of this information? Why didn't they respond if they did know? This seems like a predictable design flaw. Was the unsafe interaction between the two requirements, preventing liquid from entering the flare and the need to discharge gases to the flare, identified in the design or hazard analysis efforts? If it was identified, why wasn't it handled in the design or in the operational procedures? If it wasn't identified, why wasn't it identified? It's an obvious flaw and an obvious hazard. Here's another example from the same accident. The event was that the continued warming up of the reactor caused more chemical reactions to occur between the ethylbenzene and the catalyst pellets, causing more gas formation and increasing pressure in the reactor. Again, that's just what, but it doesn't tell us why. So we need to answer these kinds of questions. Why wasn't the increasing pressure detected and handled? If there were alerts, why did they not result in effective action to handle the increasing pressure? If there were automatic overpressurization control devices, for example, relief valves, why didn't the relief valves work? If there were not automatic devices like relief valves, why weren't they included in the design? Was it not feasible to provide them, or did someone just make a mistake? Those are the kinds of questions we need to answer. Let me give you an example of a real accident. This is a workplace accident. It was a large manufacturing plant, a company manufacturing large things. I can't give you the details, but they were assembling a large complex product. There was a specific part that wasn't available when they needed to put it into this thing they were assembling. So that a decision was made to add it later and not slow up production. The part finally did arrive, but to get that part into this thing they were assembling, they had to disassemble a large piece of the product. So how could they do that? Well, they needed scaffolding. So they had some scaffolding produced and created during the shift before this one. And when they went to remove that large piece that they needed to get to remove to put in the new part, the scaffolding kept it from being removed. They couldn't take off that part, that big door. It was actually a big door. So what did the workers do? Well, they took floorboards out of the scaffolding so they could open the door. They removed that piece, and 4 workers were holding the door, the piece, while they moved it to the end of the scaffolding to take it down to the shop floor. All 4 turned and 1 fell through the hole in the scaffolding. So the company accident report used a causal analysis tool, really useless thing that lots of people use and probably many of you use. And it came up with the answer. The error was that the workers stepped in a hole. Well, that's pretty obvious. We know that. Why? Well, they said they made a mistake and they had a lack of situational awareness. Well, of course they made a mistake. They stepped in a hole. That's a mistake. The lack of situational awareness basically is just fancy language for saying they didn't know that the hole was there. Well, of course they didn't know that the hole was there. They wouldn't have stepped in it if they'd known it was there. So clearly this is not useful. This is providing no useful information except that we can blame the worker, which is what they did. They identified the root cause as worker error and the lack of experience in doing the job. They hadn't done it before. They didn't know there was a job aid for this job. And they didn't perceive any unusual risk and didn't ask for help. The recommendations then, and that's all the accident report said. The recommendations were tell workers not to remove scaffolding, floorboards from scaffolding, add the tool information to the job instructions, and during a daily kickoff meeting, discuss the potential hazards and ensured safe work practices for assigned tasks of the day. Well, come on now, they're not going to every morning come up with every single thing and discuss every single thing that workers might do wrong, including removing floorboards from the scaffolding. They would be there all day and they would never get any work done. That's just silly. But it allows them to focus on the victims and the workers themselves instead of trying to look at the larger issues. So what kinds of questions should the report have asked that it did not ask? Why were they doing a job for which they had no experience and without oversight from someone who did have experience? Why didn't they know about the proper job aids? Whose responsibility was it to ensure the right equipment was available and used? Why did they not ask for advice when the scaffolding prevented them from doing their job? It turns out this is a cultural problem in this company. The company has a motto, find a way. And they basically tell people, figure it out. find a way to do the job no matter what happens. And so that's what these people were doing. They found a way. It wasn't a safe way, but they found a way. Who provides oversight for out of sequence work? Sorry, this was out of sequence. It was, the part came late and it wasn't done when it should have done. Does anyone provide oversight for that? Why was there no hazard analysis done for out of sequence work? Why was the blame for not understanding the risks involved placed on the workers and not on their supervisors? Why was the incorrect scaffolding for the job constructed in the first place? Why were the people constructing the scaffolding not aware of what type of scaffolding was required? Who evaluates the hazards of out-of-sequence jobs? It turns out nobody does. Was there documentation of tools needed for the job? Why was the job not done when it originally was supposed to be done? Well, that's a supply chain problem. And in fact, the problems really go back to the supply chain. So I asked, does this happen a lot? And they say, yes, they have a lot of problems with their supply chain. They use a lean thing just in time. So they have a lot of supply chain problems. There was supposed to be a meeting about how to accomplish the work that was needed, but it was never held. Why? I don't know. I couldn't find out. Why didn't the work wait until it could have a meeting? Our workers often expected the jury rig make up solutions with no oversight or input from others. All of these are important questions to answer in order to be able to figure out why this actually happened and how to fix it. So a new accident model, and the one that I came up with, is called STAMP, and it treats accidents as a dynamic control problem rather than a failure problem. So hazards and accidents result from the lack of enforcement of safety constraints on system design and operation. Losses involve the interaction of humans, physical components, software, organizational factors, regulatory factors, culture. All of these things contribute to accidents, and we can only fix the problem of accidents, get rid of accidents, unless we look at all of the interactions of these different components of accidents. Controls are created to prevent hazards. Accidents occur when the controls are ineffective, not when failures occur, but when we don't have controls for those types of failures. So CAST is an accident analysis method to help increase learning from accidents and incidents. Its goal is to minimize hindsight bias, to provide a framework or a process to assist in understanding the entire accident process and identifying systemic factors, not just providing an excuse to blame the operators. It tries to get away from blame, who, and to shift the focus instead to why and how to prevent it in the future. We need to determine why people behaved the way they did and the weaknesses in the safety control structure that allowed the loss to occur. It's a structured technique that helps to generate the questions to be asked. And it's a change from what we do now. The goal is not to start to look for failures or human error. The goal instead to ask, why didn't the designed controls prevent the accident? We all try to prevent accidents. There are lots of controls provided, government oversight, there are rules, there are all kinds of policies. Why weren't these effective? And what changes are needed in the controls to prevent future accidents? We need to identify how each of the components in the control structure, everybody involved contributed to the loss. And I already said the last one. So there's 5 steps in CAST. It is a structured process with a set of steps, and you go through those steps and then get the answer. So you need to first figure out where the system boundary is, what hazards, what constraints, what events did happen. We do need to start from events, what the physical loss was, and so on. Then we build a model of the safety control structure, how accidents are controlled, and then analyze each component in the loss, the contributions to the accident, what mental model flaws. If it's humans have models in their heads of what they think is going on. And accidents often occur when the mental model is different from the physical, actual, real thing system. We need to look at the context in which decisions are made and again, generate questions. Then we need to identify the control structure flaws, and that may involve communication, coordination, the safety information system, the culture, the changes and dynamics in the system that have occurred, economics, environmental constraints, and so on. And we actually do have, if you're interested, one of my Japanese students did a CAST analysis of Fukushima Daiichi. And what you find is that the whole structure of the nuclear power system and controls in Japan were flawed. And of course, you know that lots of changes were made after the accident. And then at the end, you create an improvement program with recommendations and feedback. So here is don't have time to go through all the details, but this is an accident in a chemical plant. This is the one I was talking about. It was a Shell plant in the Netherlands. And there is a chemical process here, which had above it, there was a automated process control system. There were also operators who were interacting with the automated system, but also controlling the process, the chemical process directly. There was safety management in the plant. There was plant operations. Above them, Shell in global has a projects and technology, which actually designed this plant. They have safety management. They have above, like any company, executive management. At the same time, there was oversight in the Netherlands. The government agencies oversaw operations in the plant. And above them is the European Union, and they have rules and procedures. The oversight agencies also oversaw emergency management, state and local emergency management and public health, which here's a picture of the explosion, which went into effect after the accident. And in fact, if you look carefully at the accident using CAST, you find that every single one of these things contributed to the accident. And though the operators are mostly blamed, they had the least impact, in fact, on the actual accident cause. So we start by looking at the hazard, exposure of public or the workers to toxic chemicals, the constraints that must be enforced. The workers and public must not be exposed to potentially harmful chemicals. Measures must be taken to reduce exposure if it occurs. Means must be available, effective, and used to treat individuals inside or outside the plant. A second hazard is just explosion or fire. and chemicals must be under positive control at all time. There must be warning and other measures available to protect workers in the plant and minimize losses to the community. And there must be some means to respond to explosions that actually occur. In CAST, there's a format that you look at, and you take each component of the system, like the process control system or safety management, and identify their responsibilities, the unsafe control actions that occurred, what did they do that contributed to the accident. But then we don't stop there. That's where most people stop, is we say they didn't do, or they did X and it led to the accident. But that's only where we start in CAST. We also have to look at the context. Why did that behavior occur? What were their mental model flaws? What did they know in their minds that caused them to do the wrong thing? There has to be a reason they did the wrong thing. Everyone in this plant wasn't negligent and unskilled. They were very highly skilled. And for the control structure as a whole, we have to look at what happened with coordination and communication between the different components. What about the industrial and organization safety culture? How did that impact this accident, contribute to it? What about the safety information system? It turned out that they had assumed that this accident wasn't possible. So they gave it a probabilistic risk assessment of 0. Couldn't happen, except it had happened twice before in shell plants, actually in Southeast Asia. What? If it happened twice before, it can't be 0. But they assumed 0, so they didn't try and prevent it. That's crazy. Something is happening here in terms of getting information around the company that needs to be distributed. And there were dynamics and changes over time. So as I said, there were inadequacies found throughout the safety management system. In the physical design, there weren't the right kinds of relief valves. You saw at the beginning, they had the flare closed to prevent liquids from getting into the flare, but also that prevented gases from getting in. You saw those. The process control system, the automated system, turns out was designed not to handle this kind of problem. The accident occurred during a startup, after a turnaround, after a large maintenance action. They start restarting the plant. And it turns out that is when most accidents occur in chemical plants, is during startup or during shutdown, but mostly startup. The process control, the automated system, was purposely programmed not to help the operators during the startup, which is the most difficult time. Why? I never could figure out why. The operators acted appropriately, or at least understandably, given the context that they had. They had incorrect work instructions, which they followed. Workers are blamed if they follow the instructions, even though the instructions are wrong. That's ridiculous. Why were the instructions wrong? They were not trained to do a maintenance. There's required skill and knowledge in doing a startup by the rules of the company. None of them had those skills and knowledge. They'd never done it before, but nobody provided them with assistance from somebody who had done it before. In addition, they were provided with almost no assistance from the automated process control system. While many of the tasks they needed to do required intense attention, precision, mental effort, very, very hard to do a startup of a process. And the risks were not communicated to them properly. Management relied on the operators to see something strange and stop the process, but didn't provide the information and training to ensure it was possible for the operators to do this. So there were problems in the plant safety management. They were the ones that assumed it was zero risk, and then it said, well, my probabilistic risk assessment is zero. There were problems in operations management, in the shell designers, in the shell management, corporate management, executive level management, in the manufacture of the catalyst, which reacted badly to the ethyl benzene. Dutch regulators didn't provide oversight because this plant had been so good in the past, they didn't think they needed to provide oversight during this very dangerous operation. Emergency services actually worked pretty well. They were the one group that actually did their job pretty well. So, and there were flaws in the interactions among it. As I said, the safety information system was incorrect. The information that Shell had about safety. The culture was very flawed. There were communication and coordination problems. There were changes over time, which there always are before accidents. So unless we understand this whole thing and all of these factors, if we just blame the operators, we don't learn anything. The model we use in accident or incident analysis determines what we look for, how we go about looking for the facts, and what facts we see as relevant. This linear chain of events model promotes looking for something that broke or something went wrong in the sequence of events. They usually identify the point where an operator error, supposed error in hindsight occurred, or something physically broke, as in this case. So they blame the operators when the operators in this accident were probably the least responsible for it. Unless we look further, we limit our understanding, and we almost guarantee that future accidents related to the same factors are going to occur again. The symptoms may be different. It may not involve a catalyst and ethyl benzene the next time. So we don't see that this is actually the same accident with just different symptoms. The goal should be to learn how to improve the safety controls and not to find someone or something to blame. And we need to use accident analysis processes like CAS that avoid root cause seduction and oversimplification, that minimize hindsight bias, that are explanatory rather than accusatory, and that emphasize a broad contextual view of human behavior. Why did the person think it was the right thing to do at the time? So CAST provides this structured process for learning more about accidents. It helps you generate the questions that need to be answered during the investigation and identify the information that needs to be obtained. So that's my talk about CAST. But I was also asked to say a few words about STAMP and specifically STPA. I know that most of you are more familiar with STPA than you are with STAMP, so I'm going to assume that you know what STPA is, but it's a proactive accident analysis technique, hazard analysis technique that you use before you have an accident. CAST comes after the accident, but you'd like to prevent accidents, so you try and do STPA to identify the scenarios that can lead to the accident. And STAMP, which I mentioned before, is a new causality model, and it allows the use of development of new tools. You heard about CAST. I said the hazard analysis tool called STPA. We can do security analysis, and I'll mention a little bit more about security. Organizational cultural risk assessment analysis. You don't just have to look at the engineering parts, you can look at the social parts of systems. We can identify leading indicators. Usually there are hints of accidents before. There are precursors that don't have a serious effect until eventually all the conditions come together and you have an accident. How do we identify that the system is that changes are occurring that are increasing risk to an unacceptable level? And how do we, and so we have some tools that will help find things, changes that are occurring before you actually have a serious accident. And of course, then model-based system engineering, we have tools for. All of these we can put together into new processes of system engineering, risk management, regulation, and so on, operations. I want to make a couple comments because I find a lot of confusion in the world. So let me explain some of the confusion I see. A lot of people, oops, that should have been cast, think that you should combine STPA and CAS, that should be, or STPA with additional analysis techniques. And so they propose, well, we should do STPA and fault trees, or STPA and failure modes and effects criticality analysis, or STPA and whatever, attack trees, which are just fault trees. The problem is that, in fact, if you look at it, we can show this empirically, I can show this mathematically, and we can show this actually in practice. The stamp-based analysis tools are much more powerful than the traditional analysis tools. So the scenarios generated by STPA are more than the scenarios generated by the old traditional hazard analysis. It makes no sense to spend a lot of resources. In fact, they're more expensive to do the traditional ones, to waste a lot of resources to find the same things that you would find with STPA. It's just a waste of resources. You can do it. I don't care. I just don't want people to waste their time and energy, because then you can't do as good a job. So it makes no sense. This is a different paradigm. It's a different kind of approach, STPA and STAMP, based on a totally different accident causality model. And it's much more powerful. It includes everything that would be found by the traditional analysis methods. What about cybersecurity? I know most people are interested in cybersecurity. This works for cybersecurity too, but it, like accidents and safety, it's a paradigm change. It's a change from what's done in cybersecurity today. It's totally different. To explain this very briefly, most of what we do in security today is look at attackers, try to keep people out of systems. You cannot keep people out of systems. We need to learn that. It doesn't work. Anyone who wants to get into my computer is going to get into my computer. And that's true of all the secret government computers and all these supposedly highly protected computers, because all of my information has been stolen from all these computers. And so I know you can't keep people out. What you need to do, and what the STPA security approach says, is forget about keeping people out. We need to make sure they can't do anything horrible when they get in, that they can't get the information, that they can't do the wrong thing, that they can't trip the nuclear power plant or do whatever. The other thing is that STPA and CAS can be used for the social and organizational aspects of systems, supply chains, management, decision making, security and safety both involve these social and organizational aspects. Unless we handle them, we cannot handle safety and we cannot handle security. But the traditional approaches do not do that. So STPA is being used today in many places. I have hints about other countries, but of course, nobody will talk to me. I know they're using it, but I know for sure that the US Air Force is using it on a lot of projects today, and it's been very successful. And here's just one example of the success. I assume that you've heard of SolarWinds. SolarWinds was that big break-in into the US Department of Defense computers that was just a disaster not too long ago. Well, it turns out that STPA security SEC was applied to one DoD. See if I can get rid of this. I probably can't. I should have done this beforehand. Nope. I don't think it's yet. Well, it was applied to one DoD program before the SolarWinds attack. Only one program in the DoD, not the whole DoD. It was applied to one program, and they looked at the whole control structure, all of the social and physical systems, the program office, the supply chain security, the program buyer, the vendor, the program receiving and stores, the operational system and support. Often we only look at the operational system and support. So the program, here's the bottom line. The program that used STPA, by this way, this was done by 3 people, Michael Baer of BAE, John Thomas from MIT, and Colonel William Young from the US Air Force. And the program that used STPA was protected from SolarWinds. It was one of the few DoD programs that SolarWinds could not attack successfully. And they found the vulnerabilities that SolarWinds took advantage of before SolarWinds and fixed them. So the things in blue were vulnerabilities that were later exploited by SolarWinds attackers. The orange are ones that were found by STPA, but didn't have to be exploited in this attack. And you can see at every level, this STPA was able to find the things before they happened so they could be fixed, the vulnerabilities. This is astounding to me to see this real data, this real program, because SolarWinds was very sophisticated and it caused a lot of damage in the United States. So what about what's happening new beyond security in STPA? Well, there is a new SAE standard. It will be available in January. It's been approved. And it's a recommended practice for STPA in automotive applications, but the same standard can be used in defense and aviation and other things beyond automobiles. But this is now by the SAA recommended to be used STPA. We're working on some new problems that we haven't tackled yet. One is analyzing complex teaming relationships between humans and automated systems. It's not just now, we're building so many automated systems, robots and other kinds of automated unmanned aircraft. And it's not a simple relationship between the human controlling the automation. They may be, in fact, in parallel, cooperatively trying to control a process. We don't have any hazard analysis techniques to do this. Don't even think about it, starting with fault trees or these other things. Forget it. STPA is possible to do it. This will be a PhD dissertation that will be available in about 6 months. We're looking at AI, machine learning, and hazard analysis. People want to add machine learning into systems. How do you make it safe? Healthcare safety, we're doing a lot in now. More in security. We're doing safety analysis during concept development, early development, to build safety into system design versus trying to assure it afterwards. And our test case and the test platform we're doing is urban air mobility and unmanned aircraft and manned aircraft in the urban environment, small aircraft. We're looking at applying STPA to test and evaluation. It's been done, but we need to have a more rigorous investigation of it. And the risk matrix, that's the red, green, yellow chart that people build, doesn't work. I mean, you can't get likelihood, especially early when you don't even have a design. So we have a new way of developing a risk matrix that we believe is more effective. It scales to very large systems. We've been using all of these things on the most complex systems that humans have tried to build. Many of these are defense systems. And all of these techniques work on these incredibly complex systems that the other techniques just don't work on. You would be crazy even try some of them on it. What about evaluations and return on investment? There have now been hundreds of evaluations in comparison with traditional approaches used now. Some have been controlled scientific evaluations, some have just been empirical industry uses. Everyone shows that STPA is better, that it identifies more critical requirements and design flaws. As I said, it finds everything that the old techniques find. Everyone that measured showed that STPA requires orders of magnitude fewer resources than traditional techniques. STPA can do more in 2 weeks than the old techniques can do in months of effort. That was a big surprise to us. We're only now starting to see return on investment estimates. Companies don't like to report these, but one large defense industry contractor claims that they're seeing 15 to 20% return on investment. That's of 15% to 20% of the entire cost of the program when they use STPA. Why? Because you find errors early and you don't put them into the design. You design a safe system from the beginning. Much of the, cost of development is in trying to back up. When you find an error, you have to go back, and that's astoundingly expensive. So you want to find things as early as possible. Is it practical? It's being used, I think, probably more like 90% in automobiles today. Aircraft and spacecraft, extensive use. Defense systems, some of the newest defense systems. This middle one is the replacement for the Minuteman missile system. This is future vertical lift future helicopters for the Army. It's being used in these systems today very successfully. Ships, marine, air traffic control, and so on. In our last STAMP workshop last June, we had 2,316 registrants from 85 countries. This is now being used by thousands of people. It is not just a university, my little thing. It is now being used everywhere, and there are new international standards, as I said. So I'm finishing. there is a website. You can get lots of information and you can get some free books. First is my book, which was published, but you can get a free download. And I'm sure they'll publish this presentation on their website of the conference, so you can get these URLs. The STPA handbook, which was put up on the web in March of 2018. It's had now more than 100,000 downloads in the last 2.5 years. It's been there. It's been translated into Japanese, Chinese, and Korean versions, so you can get a Japanese version. There is the CAST handbook is newer, and we don't have a count of how many downloads, but it's been translated into Korean and Japanese, and these are all available at this website.